So is everybody enjoying the conference so far? I mean, yeah, it's good to meet a lot of you. I think I've worked with many of you over several years at this point, and I've never gotten a chance to meet many of you, like Kevin here. Yeah, yeah. I know my picture's changed, so. Yeah, I'm gonna go ahead and get started here. So yeah, my name is Tom. If you don't know me, I work at Intel now, which is great. It's a wonderful company. This is my talk about real-time I/O, or a block stream API, not a blockchain API, for Zephyr, or really IOU ring for Zephyr. So I've used Zephyr now for 2 or 3 years, off and on. I ran into problems when I tried to use it previously with as a contractor developing small little IoT devices, and really it came down to a couple of problems that I ran into, and I'll have a little story about that. But the problems that I really had were, blocking I/O requires threads always, right? Async calls in Zephyr are wildly varying. I say underdefined here. Really, I mean they're varying in behavior and how they operate. And there's not a lot of application control over when to use DMA with, say, like a SPI bus. You do a SPI transceive, and it just goes off into the SPI driver. You really don't decide, hey, I'd like to use DMA for this really big 4 kilobyte FIFO transfer I'm doing off my sensor. And callbacks are great. We all love callbacks to some degree, but they get complicated once you start trying to chain a bunch of them together. You got to carry along the state of what you're doing along through those callbacks. That can be a little frustrating. And of course, copying is wasteful. Memcopy has got to be the most useless waste of time ever, right, for a microcontroller. So where did I run into this problem? I ran into this problem doing this project. It's the Boss. It's a pitch training tool for baseball players. The idea here was to save people from Tommy Johns while getting them to go faster. Tommy Johns, if you don't know, Major League players, it's like a huge dynamic motion, super fast, all their tendons, muscles getting torn up every time they throw the ball. So this tool was meant to kind of help people avoid that by training them to pitch faster, less injuries. So a quick little video. Woo, that was fast. That was a college player. And yeah, there's the data already on the phone, which is wonderful. So what happened in that device to get all that data and try to build rebuild a kinematic model of this guy throwing a ball in a couple seconds, if that? Well, I needed to collect a lot of sensor data, sensors from that had varying ranges of acceleration ranges, up to 100 Gs, in fact, to actually capture the highest parts. And yeah, it's pretty wild. So I mean, in this little ball, there's just a little Nordic NRF52 Bluetooth SoC. It's wonderful. There's 4 sensors on 2 different SPI buses. The whole pitch motion, right, is maybe 2 to 3 seconds altogether. But the big part, the big motion part, is maybe 30 milliseconds. So this part from back here to here, 30 milliseconds. And I'm trying to capture as much of that data as I can to rebuild the kinematic motion of the body. So I really wanted to use all the RAM on this little tiny chip for capturing that data and then shipping it off to the phone, as much of the RAM as possible. Because the more RAM I had to use for the sensor data, the faster I could collect it, the more I could collect, the better my analysis of that motion I could get. The CPU time in that brief moment is really trying to capture a pattern. And the pattern in that case is actually 2 parts. There's the pitch start and pitch end. So that trying to capture the moment that the pitch is over, take that collected data, ship it off to the phone as fast as possible, where an app can actually do the work of trying to rebuild that kinematic model. And because there's 4 different of these sensors, trying to collate them and align the timing of the samples is of course tricky. There's no clock. I don't have a nice clock aligned to all these sensors to say, okay, everybody sample now. I didn't get that. You basically say, okay, start sampling at a specific rate, and then you get the data back, and it's up to you based on the interrupt time try to align those. So what did I end up doing to get this to work? Just to briefly say, like Zephyr out of the box didn't work for me, unfortunately, in this case. It just didn't. So what I had to do to get it to work was I had to, in my sensor interrupt from the GPIO lines, I started my SPI transfers. And by default, if you try to do that in Zephyr today with any of the SPI APIs, it won't work. There's a semaphore there, forget it. And I wanted to do that because it would save time and RAM. I didn't need a bunch of threads going out to each SPI device collecting data. I just needed to start a SPI transfer. The SPI device already does all the work for me. Just need to say start at the right time. And I use DMA to save up time. So in this case, it's a Nordic chip. So there's a great little Nordic SPI M driver that does easy DMA, which is very easy. And to collect the FIFOs and free up all the CPU time to try to watch for that pattern. Last bit is, I would collect the timestamp of what all these sensors are doing to again align my samples up, all in the goal of building a very nice kinematic model of what the body was doing. This all required forking of Zephyr, which is unfortunate, and I'd like to save you all from that. So the essence of the problem that I ran into really is there was no way to do IO the way I wanted to do it when I wanted to do it. So of course the solution is queues. It's always queues. And kind of getting back to this idea, the peripherals are already concurrent, right? You tell any IP block, or well, I shouldn't say any. There's probably IP blocks that don't work this way, but most IP blocks that I've personally worked with, you write some registers and you wait for an interrupt. There's really no need for a thread to do that. It's more like a little actor in a box. You send it a message, you get a message back when it's done. So in this case, the idea here is to submit requests to peripherals, and you receive completions. And this matches up, crazily with DMA and the way DMA works in a lot of places. DMA works by, in a lot of ways, you can assign transfer lists, right? You can create this cool little thing, transfer list. Hey, I'm going to go write out these 256 byte blocks to my audio codec, and you just ship that off to the DMA controller. Here you go, DMA controller, go do the work for me. Matches up very well with that. So what is RTIO? RTIO is really a pair of queues. And maybe broader than that, it's a context of asynchronous execution, not across just one peripheral, but all the peripherals that you choose at the time that you want to use it. You can do that. The input is a queue of submissions, and this comes from IOU ring terminology. The output is a queue of completions. These are atomic queues. There's single producer, single consumer. We'll get to that if we want to, in the discussion area if we want. There's two APIs that anybody can implement as part of this subsystem, this API. There's a executor, which is here at the bottom of this little tape drawing that I created, and at the top, and there's also an IO device. So the executor is sort of tasked with, here's the queue, figure out how to make this all work for me. And the IO devs are really trying to abstract over like a one particular IO device. So maybe your SPI device, maybe your I2C device, maybe your sensor. And last but not least, yeah, this is really based on IOU ring. So a lot of the terms, the APIs, the way you use it is really based on IOU ring. I did that very intentionally. IOU rings seem to match up really well with what I was trying to do. So how can you use this idea of applying queues to software or to IP blocks and peripherals, all this fun stuff? Well, we can do simple submissions. So we can say, hey, sensor, go read your FIFO. And that's great. I'll get the FIFO back at some point. If I say, hey, sensor, go read your FIFO maybe 4 times in a row, that's great too. Like each time maybe I get a FIFO watermarked ISR, it takes off the queue, reads into it, gives me the completion when done. The same could be true with an audio codec. Right here, here's 4 blocks of data. Go write it out to the codec. give them back to me when I'm done. In fact, the I2S API in Zephyr, the few implementations I've looked at actually use queues in that way. They just hide them from you. So a few things about this is, yeah, the ordering is only based on the order of things that you've put into the queue. If you put in, 4 read or write operations, whatever it may be, they're going to be sent to those IO devices in the order that you put them in there. So if you put all 4 of these things, in this case, reads the same sensor, they're going to be done one at a time from that sensor. And the executor is in charge of making sure that it's only doing one at a time. Oops, going back. Yeah, and last little bit about this is failures don't cascade, right? So if I put 4 things in the queue, needless to say, if one fails, the other 3 are not going to fail in my 4-item queue here. So what does this kind of look like in code? I think it's kind of nice to look at. This is the actual the happy path test case for this. And I set up an IO device. I acquire my submission queue entry, which is again an IO U-ring term from my submission queue. So there's no allocating. It's not like a K-FIFO where you have a list pointer at the top. It's just a simple SPSC atomic queue that you pre-allocated. And then you can configure it however you like. In this case, I'm configuring it to do nothing because it's a test case and I don't really need to do anything. It's not a real device. And this is kind of the interesting bit. When you actually submit these items from the queue to the context, you give it the number of items that you want to wait for potentially. So in a lot of cases, if you're in a thread and you're like, okay, I'm going to go read some data from my sensors, maybe you put 4 things in the queue, but you only really need to wait for 1 before you start dealing with processing it. Or maybe you're doing a submission straight from an ISR. You've done some things, now you're going to submit again. Don't wait for anything. Wait later when I go to get the completions out of the completion queue. You can do either one of those. Those are both acceptable. So yeah, last bit here is, we're gonna consume from the queue, take a look at what it's there, and release it. So it's very much kind of like a malloc free out of atomic queues. Pretty simple. So what about if we want to do things in a particular order, or we need something to finish before the next thing starts, and if the first thing fails, well, the rest of these things need to fail. Well, that's where IO-ring link or chaining comes into play, and so that's really what I've also done here. So here, we have a queue of 4 items, and you can imagine maybe this could be like an I2C device being configured, or perhaps a FIFO being read, where maybe you do a write of the address you want to read back in the second one. Those are all possible. And this is these orderings are enforced across devices in this case. So you could have multiple devices where I'm going to read from my I2C device, read from my SPI device, and then write to flash, perhaps. Those are all possible things that you can do with this API and the way it works. If any of these things fail, they're all going to fail. All the subsequent submissions are going to fail after it. So 0 succeeds in this case, 1 fails. Now 2 and 3 are immediately failed. Makes sense. So what does that look like in code? Real briefly, kind of the same thing. I mean, we get some submissions, 4 of them in this case. We mark them as chained with a little flag, and then we submit all 4. We wait for all 4. We consume all 4. Wonderful. They've all succeeded. You can imagine the failure case. Not too hard to imagine, I hope. So now what happens when we start doing this, right? We start saying, okay, well, what if I want to do multiple linked entries? So I have maybe two sequences of things that I want to do. And now this is kind of interesting. Things get in IO U-ring, these things can happen concurrently. And what ends up happening is in the Linux kernel, and the way that works in the Linux kernel at least, is you submit this thing, it sort of creates these linked list queues that go independently of each other, and you can set points at it in the queue where, okay, I'm going to wait for everything to complete a flush, and then everything after, then it's sort of like a convergence, right? Like all these things, concurrent operations, wait, continue on. That's all possible. But I think the kind of the interesting part here is, at least for Zephyr, these things can happen concurrently. And what does that mean for us? Well, that means, hey, maybe I have 2 SPI buses with sensors on them, and I want to go read from 2 SPI devices at about the same time. Obviously not exactly at the same time, but I'm going to start them at the same time, approximately. You can do that with a single function call here. You set up your queue, say go, and you wait. Well, what happens if any of these things fail? So the failures are contained each chain of operations. So if 0 fails, only 1's going to fail, not 2 and 3. That I think makes sense. Yeah, and I want to kind of pause here and ask if anybody has any questions. I think I've covered kind of a lot here. I just want to, yeah. Are there any questions so far? Yeah. Yeah, so that's a great question. So I mean, like this, yeah. So internally, you get two ring buffers. You get 2 single producers, single consumer ring buffer queues with atomic in and out values. So this whole thing, this picture right here, this is really one ring buffer, and each item in the ring buffer is saying, hey, the next one in the ring buffer is linked to me, and I must be 0 must complete before 1. Does that make sense? Any others before I continue? Yeah. It does. So yeah, like, I mean, it does require a little management, but I kind of come back to this picture here, and that is absolutely an intent of this. So you, in getting these completions, you can resubmit the same submission one after another, and so that kind of again feeds back into DMA. Does that answer the question?
Like, you do it without like any time.
Right, so just like automatically. So you say at the very last item, okay, just go ahead and repeat this chain. Not at the moment, but that is a good point and a good thought. It does make sense, I think, in the case of like, right, trying to map it to hardware, to DMA. You want to map this chain of requests to DMA, perhaps. Yep.
What about, are you worried about collecting or developing?
Yeah, I mean, so that's kind of an interesting question. I mean, I am, but the submission itself, like that struct that I'm giving to these queues is really, and I like, again, I go back to IOU ring and how that works. It's really a big fat union of anything you want. So you could create like an abstraction over like a DMA buff, for example, right, where you sort of what you like. Oh, this DMA buff is perfectly fine on core 1 because the decache is good, and on core 2, well, not clean, right? So now you need to do the invalidation. Yeah, I mean, you could totally do that. I have that thought in my mind as well. At the moment, no, like it's sort of like a proof of concept. I'm really trying to map this idea of IOU ring to Zephyr, and I think that is where I want to go, right, with it, because it makes a lot of sense. It just makes a lot of sense. So yeah. Okay. So I'm just going to keep continuing. We can talk more at the end, I think. So does this solve like the problem that I initially had? I think it does. I definitely think it does. I have this predefined set of operations I can do in ISR sequences. It's effectively a chain of ISRs. I don't need a thread at all to go read from a sensor or write to an audio codec or read frames off a camera necessarily. I can do all of that just with ISR chains and setting that all ahead of time, hitting the go button, right? And applications don't really need to deal with trying to write directly in the in your server, ISR routine, so you don't have to deal with the constraints of that yourself if you don't want to. The API itself is friendly to it, though. You can submit from an ISR. You can even consume from an ISR, though it's probably not a great idea if you're just going to be spinning there for very long. But you could do it. So if you have like this crazy setup where right, your nested interrupts, like, okay, I'm going to submit some things, but I know my nested interrupt has a higher priority. I can just let the interrupt go, have a little polling loop, and I know by the time that actually it comes back, it'll be done, right? I can do that with this API, no problem, which is kind of cool to think about. That you could just have all this stuff going, and your main thread is just sitting there doing absolutely nothing. I think. Yeah. So yeah, we still get the benefits of reduced thread counts and precise timing of doing what we want when we want to do it this way. DMA is sort of like, there's lots of options here, I think, how to map this to DMA. There's really kind of two things that have come to my mind, at least. And one of those is submissions may just directly include DMA, right? So maybe the IO device where you're reading or writing to is just directly the DMA controller that you want to work with. The other option is that maybe the executor, you write a custom executor that knows how these devices interact, which DMA controller you want to use, so you can map your reads, writes, your IO operations to DMA in your executor, if you like. So I think those are two perfectly valid options. I don't know which one is better yet. Kind of interested in your thoughts on that. But is there a Zephyr fork required to do what I wanted to do anymore with this API? Absolutely not. Absolutely not. So with new solutions come new problems always, right? The current bus APIs, they're pretty abstract already. They already kind of abstract over what a scatter gather looks like from SPI, I2C. You give it a list of things you want to send, write, read, and you say, okay, do my transfer, do my transceive. The current APIs aren't going to be, I can't just wrap over the current APIs in a lot of cases, probably. The current async function behavior is also kind of interesting in Zephyr. A lot of them, may or may not work from an ISR. So in a lot of cases, they probably wouldn't work from an ISR, and that may be surprising to some of you. But if you were to go do a SPI transceive async with most drivers today, there's going to be a semaphore that's held. And if you already have one going on, it will block. So don't do that from an ISR. Other APIs don't do that. So I believe it's LoRaWAN. You can just read write to LoRaWAN all you want with the async API, and it'll tell you it's busy. It'll return, negative error, no busy instead of blocking. So the behavior is kind of different, depending on what driver class you're looking at in Zephyr. And then, kind of going back to this whole idea of, well, we have an IO dev and I'm just going to submit operations to it. Well, what happens if the thing is busy? So you have one peripheral, you have one SPI bus. Maybe in one thread, you want to do some blocking, SPI, reads, writes. You have this RTIO thing. Okay, great. I'm going to go do some async reads, writes. That's going to be unpleasant. Basically, what we need to do there is probably have something like an async mutex where, I say, okay, when you're done, give me a call back so that I can start my request chain again. And I really want to start somewhere useful. I don't think it's, I don't think it's a good plan to try to like rewrite the world here. I'm not trying to do that. I want to start somewhere really useful to people. I think the useful places are really higher level, I should say, devices where this actually makes a lot of sense. Like we were just talking, Pete, ADCs are great, sensors, video, audio, I think make a lot of sense to try to do this sort of like streaming API where you stream blocks of data in or out of it. Iterate from there, and then maybe go downward, depending on where things go. So yeah, I'd love to talk to all of you about this. I really want your feedback. My GitHub handle is there. It's TEBird. The GitHub pull request is, I thought this was really great. It's the 44,999th pull request, which is actually really cool to see Zephyr have so many. I think when I first submitted my first PR to Zephyr, it was in maybe the 10,000 range. Yeah, it is absolutely amazing, absolutely amazing. And I had Maureen, thank you, Maureen, I think create me a Discord channel early on this, which was really quite nice. So please come talk to me on Discord about this. My Discord handle is Tom B or Tomb. And that's it. I'd love to hear any more questions or thoughts that you have on this. Yeah. The completion queue. Yeah. Yeah. So that. Yeah. So the completion. So yeah. Okay. Let me. Can you? I want to be sure I'm thinking about this right. Can you repeat that?
Please repeat the question.
Right. Yeah. So what happens? Oh yeah. So what happens when a completion queue entry gets popped off the completion queue. Yeah. So would the completion queue block until that submission has completed, right? And these are IOU ring terms. I know it takes a minute to get a handle on them, but that's actually up to you. So there's and the way it's implemented today is you can block. So there's you can block or spin or do, if you get a null pointer back from it, you can do nothing. But there is a blocking call. So there's a RTIO. CQE, get, wait, something along those lines. Sorry, but yeah, there's an option basically to wait on an optional built-in semaphore. So when you get the completion, that semaphore gets set. You wait on it. So you can block either on the submit call or the completion queue. Either one is perfectly valid, or you can block on neither and pull. You can just sit there polling. Yeah, Andy, what's up?
I think the question was more is the callback the sacred question. Pull off to do your callback, return the callback, go to the next site. A callback takes a long time.
Yes, yes. So don't do that. Don't do that. Yes. That is exactly the intent here. So just to repeat, so to rephrase what you're asking me, when you submit a submission to an IO device, it is a blocking call in the ISR. So the first one happens right when as soon as you do submit you have this queue of operations and it effectively starts all the concurrent things. But then on the next one, when it completes, yeah, the next thing gets started. It submits the next object request to the IO devs right in that same ISR, which is really quite nice in a lot of ways, right? Because most of the time, and for the targeted intent of this, that makes sense. You're going to write a couple of registers like, okay, spy, like here's the bytes that I want to write, and hit the bit flag that says go. Well, come on, that's a couple operations on most of these devices. It's not going to take very long at all. It's going to take less time than switching to a thread with a semaphore. It's not a huge, massive improvement, but it is an improvement over doing the context switching involved there. But yeah, you could. So it's not that you can't do it, but just know that is a inline call. So if you wanted to do it where you had a longer operation, so maybe you create like a custom IO device with a process in that queue of things, and you want to process something there, you can still do that. But what you'd have to do is, probably use a thread or work queue, and at that point submit, either like set the semaphore or submit the work queue task to then go do it. And then when that's done, then you tell the asynchronous execution context, hey, I'm done, go to the next thing. And that is perfectly valid as well. Yeah. Awesome. Yeah. Yeah. Yeah.
Pluggable executor.
Yes.
So is that something you have to build code yourself, or use like the work queues that are called?
I've written two for you. So there's a start, and one of them is basically it just does one after the other. And the benefit of that is the code size is incredibly small. It's like 400 bytes of ROM, so quite tiny. The concurrent one where you try to do multiple things at the same time, that one's a little bigger, maybe 1400 bytes of ROM, and it requires an extra, pointer and byte for a status of the task. So it's like, rather than, I know most of the things in Zephyr, right, we use list for, but in this case, I used fixed size queues. And so there's a fixed number of concurrent tasks that you can tell this particular executor, hey, I only want to care about running 4 concurrent things at a time. That's settable with like the macro. Basically, you have a macro that statically allocates this thing. You say, okay, I want to have up to 4 concurrent tasks. It will allocate an additional, 4 words of memory for pointers, and then 4 bytes for status register, like for a task status. But that, yeah, that works today. I have tests for that. So there's at least a very simple one that just does one thing after another. And then the concurrent one, you can send these chains of operations and it will go. Yeah. Yeah. Yep.
So what's the path to getting everybody on RTIO? Like, I mean, are there thoughts to standardized frameworks taking existing drivers and APIs that are callback in ISR based or blocking or whatever, so that there can be on the library, so that they implement what they've got now in terms of RTIO and then up with that RTIO in the middle? You know, what's the fit?
I think so. Yeah, I think so. It's a bridge to build, still, for sure. But I think so that like part of that is sort of fixing the inconsistent, like to kind of go back to Anas's keynote, the inconsistent async calls, how we just do things kind of wildly different depending on what peripheral we're talking about with async calls. I think if we just had consistency over the async calls, I think a lot of the other things could be worked out. Even if, like, ideally in my mind, for like bus transactions, you would do like one message at a time, like kind of like start transaction, read write messages, stop, end transaction kind of thing. And that's just not the way the APIs work today. That's okay. What we could kind of like say as well, the existing APIs are more like vectorized IO operations. You give an array of things to read and write to, and that's okay. Maybe there's an operate like this is pretty flexible. IOring is pretty flexible, right? Again, it's just there's a operation code. It's a uint 8 and a big fat union that you can just kind of, I mean, obviously at some point it's gonna, you don't want it to be too big because memory. But right, you could kind of create an operation, a read v, write v, tx rx v for SPI, kind of package it all up, and if the async API for SPI were to work consistently, you could say, okay, there's a tx transceive vector operation that you want to work with against your SPI device. It could work today, given that. And you could probably gradually improve on that too, right? You could kind of move towards this, maybe ideally in my mind, move towards this, individualized start bus transactions, read write, end transaction. I think that would be, a nicer API given what I'm trying to do. Right? Is that? Okay, yeah. Well, you got me to rip on it a little bit, Andy. Thank you. Thank you. Anybody else? There are or no? Okay, well, wonderful. It was great talking to all of you. Thank you for coming to my talk. It was really exciting to be here at ZDS. Thank you.